Hello, hello. Right, hello. It's all gone green because it's time for Android. The server stuff was all in black, so we've changed color. Yeah, I'm going to talk today about guest side changes for confidential guests in Android. It's a little bit different to a lot of the stuff we've been talking about so far this morning because this is obviously not enterprise big systems. I think the Microsoft folks earlier on were talking about this machine with a terabyte of memory. I don't have a terabyte of memory in my phone. And similarly, it's different yet. Yeah, maybe next year. That'll be quite nice. It would make this a lot easier. And then the other sort of difference is we're not really relying on extra hardware support. So this is for things that are out there right now. And that means we don't have things like memory encryption, but that's okay for what we're doing. So just a quick introduction. I think I know a few people here, but I haven't met everybody. I just reused this slide from last time. So yeah, I'm an upstream kernel hacker. Co-maintain the ARM64 port with Catalin Marinas, and that's the architecture part, not the KVM part. That's maintained by Oliver and Mark. I'm in the Android systems team at Google, so we're responsible for, amongst other things, the kernel binary that ends up on your phones. And specifically, I work on pKVM, which is the hypervisor that we use in Android. And when I'm not doing that, I'm either brewing beer or catching very large trout. Okay, so a quick recap because we get everyone on the same page because this is ARM. The KVM port for ARM v8.0, so that's like the first 64-bit chips. Okay, so it uses this thing called NVHE mode. Now, NVHE mode, if you see on the left-hand side of this diagram, we've got EL0 at the top, that's user space. We've got EL1, that's kernel, and then this EL2, which is a sort of a hypervisor mode, right? And with NVHE, we can't run the whole host kernel down at EL2. Because it doesn't give you things you need. It doesn't give you enough page table bases, for example. So what happens is the host kernel, you enter it to EL2, and it quickly gets down to EL1 where it can do useful things, but it leaves behind a stub at EL2. And then later on, when KVM initializes, calls into the stub and basically replaces it with this piece of will switch code. So this is just a giant context switcher, which the host can, when it wants to run a VM or a vCPU, it can call into that context switcher and switch over to the guest on the right-hand side, and that's how it works. So you have a bit of extra latency because you have to bounce through this EL2 all the time, but you'll see why this can be useful in a minute. And when you have this mode, you have this stage 2 translation table, which I think in x86 terminology is the EPT, and we use that for the guest so that you can map physical pages from all over the place to give it this illusion, the virtualization illusion, and similarly, it means that the guest is sort of contained. So this is just normal KVM on NVHE. So with pKVM, we extend that. Okay, so we also now wrap the host in the stage 2 translation, and that's a bit strange. You think, why do you want to put the host in the stage 2 translation? Well, it's an identity map, and we're only using it for permissions. So this means we can do things like unmapping the guest memory from the host, right? Which is kind of similar to what some of these confidential computing technologies are enabling, right? And I've put this silly actual size. This makes the hypervisor look absolutely massive, like 3 kernels worth of stuff. It's tiny. It's like 100 kilobytes. It's just, the diagram makes it look massive. And then in Android, it's the same picture, but all the words change. So instead of task, we have all these Android-y type things, okay? So we have a service on the host called virtualization service. You can talk to that with Java interfaces. Behind the scenes, that's going to go and talk to CrossVM, which is the VMM we're using. Binder is what Android uses for its IPC, for applications to talk to one another. We funnel that across to the guest over VSOC. So we've stabilized the wire protocol for that. So you can call RPCs inside the guest using Binder. We have the Android GKI Linux kernel, that's the binary I mentioned earlier that we ship, that runs on the host. And then in the guest, we build another kernel from the same sources, which we call the microdroid kernel. Now, this is not, you see some folks doing these Linux tinification efforts where they try and get a kernel as small as they possibly can, and they throw out the network stack, and they throw out the console, and they end up with this tiny thing. It's not that. It's more about removing attack surface, enabling hardening options, kicking out drivers for devices we know we're not going to see, that kind of stuff. So it is smaller, but that's not the aim of it really, to be as small as possible. And then it runs a native app. We don't have at the moment any Java support in that guest. And there's this thing here called PVM firmware. So that is I'll talk more about that in a second. that's the first thing that runs in the guest, and that's critical for deriving an identity, a secret identity for the guest. Okay, so let's talk more about that. Today I'm going to focus mainly on pretty much exclusively on the guest side. So what the guest sees, the changes we've had to make in the guest, rather than the host side. There's plenty of really good talks about the host. See Quentin Perez's talk from previous KVM forum. He does a really good deep dive into the technicalities of that over there. Okay, so when we boot one of these things, we have a few constraints that we need to place on the system. So first of all the secondary CPUs have got to be off, and the hypervisor is going to enforce that. And that's pretty easy to do because we have this specification from ARM that the guest understands and the host understands, and we can the hypervisor knows about that too. So secondary CPUs are off. Okay, and the guest will request them to be powered on when it's ready. So we have a primary vCPU. The set one reg interface is limited. You can set some of the registers. We allow X0 to X14 to be set, for example, in case you want to pass some sort of parameters to the firmware. But the others are reset to poison, or I think probably 0 by the hypervisor. The memory is initialized directly by CrossVM. And as we take guest faults, we transition those pages. We do the normal get user pages thing, right? And as we get those pages, we then donate them to the guest. And so that's going to unmap them from the host stage 2 that I showed you earlier on and map them into the guest stage 2. So CrossVM still initializes everything like normal, but then the pages as they're faulted in become unmapped from the host. And the hypervisor will initialize the PC, the instruction pointer of the primary vCPU, so that we enter via this new firmware blob, this PVM firmware. And then that gets loaded on demand. So the way the host configures where the PVM firmware lives, we've got a new capability. So you can query how big it is, and you can set where you want it to be in the guest space. And if you want to know more about PVM firmware, it's written in Rust, which is quite interesting. It's bare metal ARM64 Rust. It's open source. And I think we've written a bunch of crates as part of that work. So if you're doing bare metal ARM64 Rust, go check it out, because there's things for, creating page tables, driving the GIC. There's VirtIO devices in there. It's quite a good library of stuff. And you can see here in the picture, you've got PVM firmware being loaded by the hypervisor. It validates things like the device tree, verifies the kernel, and then executes it. So I'm not going to talk too much to this slide because I absolutely don't understand all of these details. I'm not a security guy. But you can go and watch this amazing talk from Pierre Clermont, who does understand all the details from Embedded Recipes last year. The long and short of it is we have a certificate chain, and PVM firmware is provisioned with a certificate chain from the physical boot of the system, and then it can take measurements of the guest and the environment which it's in, and derive a new certificate which then the guest is given access to. And it then exposes that to user space so you can derive further certificates. And this means that if someone tampers with the guest, he gets a new identity. It doesn't not able to authenticate as it would have been before. All right, so that's the boot environment for the guest. We then have to provide some services, because it's all very well running in a private environment, but if all your memory is secret, fantastic, then you can't talk to anybody, and it's a bit lonely in there. So we've got some hypercalls, and we really mess some of these up in Android. So there's a consistent lesson which you'll see in a minute. I'm not going to upstream the mess ups, but I'd like to upstream something that's compatible so that we can run an upstream guest under Android. It just means there's going to be some funny holes in the hypercall API where we made mistakes. Okay, so there's sort of three families of hypercalls. There's a discovery, and then there's some memory sharing stuff, and there's some I/O stuff. So the discovery interface is actually pretty good. We only screwed this up in one way. So this is built on top of all the hypercalls are built on top of this spec from ARM called the SMCCC, which I think is the Secure Monitor Calling Convention or something like that. It doesn't matter. And there's a range. They go, hey, the hypervisor are allowed to use this range, and you have a UID. So KVM has a UID. That's upstream. I think it uses it for the PTP hypercall. Anyway, once you figure out you're on KVM, you can invoke this KVM func features, and that gives you back a great big bitmap of all the hypercalls you've got, so then you know what's available to you. And one of those is the hypermeminfo. So actually, this is quite a good plug. If you're upstreaming this to Linux, write documentation, because this makes it really easy to write slides. You can just dunk it in. So this is the hype mem info stuff out of documentation, KVM, wherever it is. And you can see there's some bits and pieces here. These things need to be 0. If they're not, you get invalid. Otherwise, you find out what we're calling here the memory protection granule, which is fancy speak for stage 2 page size. And you can also check if some of these memory things support ranges. We'll see those in a minute. So we've got that, and then we have another hypercall called func mmio guard info, which also gives you the stage 2 page size. So yeah, we don't need that one upstream, so I haven't upstreamed that, but we have it in Android, and I probably can't ever remove it. It's kind of harmless sitting there, though, as long as it gives the same number. Okay, so moving on, the memory call. So as I said, when memory is initially mapped into a guest, it's donated, which means it's unmapped to the host. The host can't access it anymore. Indeed, if CrossVM tries to access it, it will get a seg fault. So if you want to share memory, for example, to do virt.io, which is the main case that we're using today for this on Android, we've got this share call. So you can invoke KVM func mem share, and it's pretty straightforward. You pass the IPA, so it's the guest physical address of the memory region that you want to share, the number of granules, so you can support ranges for this call, as you saw on the previous slide. That's detectable from the discovery mechanism. And this is a bit strange. It can return the number of granules that it shared. The idea with this is that we don't want the guest to be able to get the hypervisor to process an astronomically large range, which is doing, in non-preemptible context. So we'll do a little bit, and then we might go back, and you need to resume it. We have an unshare call as well, which it's nice for symmetry, but in practice we never use this. In the future we might, but right now we're just using this stuff to set up SWIO TLB buffers. So that one I don't remember if I upstream that one or not, but it's not needed. And maybe more interesting at the end, there's this relinquish call. So this kind of does the opposite of donating a page to the guest. This gives a page back to the host, but it transfers ownership. So it's different to a share. The page is now unmapped from the guest, mapped back into the host owns it again, and the hypervisor will clear it and perform cache maintenance on it. That is for ballooning. So if you want to reclaim memory from a guest, you have to use that hypercall to drop the hypervisor's reference to the page, but also to make the page accessible so that the host kernel can use it for something else. So you need an enlightened balloon with that last hypercall. Okay, and then the last sort of family of hypercalls is the MMIO one. So by default, if you take an MMIO exit out of one of these protected guests, the VMM can't actually handle it because we don't give it any syndrome information. It doesn't know what happened. It doesn't know the size of the access. We don't give it any ability to update the transfer register, so it can't do the emulation. And similarly, we don't allow it to skip the faulting instruction. There's no mechanism to do that. So even if it could figure it out, it can't actually get off that instruction. And the reason for this is we don't want a situation where, for example, a malicious VMM, because we don't trust the host or anything in this environment, could, I don't know, convince the guest to put its stack somewhere, which is actually MMIO, there's no mem slot, right? And then you could emulate all the accesses to the stack, something horrible like that. So we have this opt-in, so the guest has to issue this MMIO guard hypercalls, and this is one we messed up quite badly, so there's a load of these. So first of all, we had an enroll mechanism, but that doesn't really make sense because when you issue the enroll call, it's kind of too late, right? You could have easily been compromised. If you weren't enrolled already, it's too late. And actually, the hypervisor automatically enrolls the guest, so we don't need that one, so I haven't upstreamed that. We then have map and unmap, but we have two flavors because we forgot to enforce that these things are 0. So that's a good lesson. Everyone knows this, right? You add a new interface, check that unused parameters are 0. You can extend them. And I know that, and people working on this know that, but we just forgot to do it. So we had to add these new ones to support ranges. And the unmap ones aren't really needed either. Like MMIO is MMIO is MMIO. Okay. 10 minutes to go, apparently, so I'll just speed up a little bit, get past some of these. That's not very interesting. Okay. Yeah, I/O bouncing via shared windows. I think most of you probably know this, but we have support for something called restricted DMA. This allows us to instantiate per device SWIO TLB buffers, so there's not necessarily just a global one, and this sort of starts to lead us towards pass-through as well, where we can say we're going to bounce for these devices and not for these ones. This is device tree. We're using device tree here. And yeah, effectively, we just bounce all of our VirtIO data through a per device SPI2B buffer. That's an early con. It's a VT100. This is a bit fiddly. So for the early con to work, we need it to be MMIO guarded before we can probe it. Like Linux prints things very early, and it's before we can do the MMIO guard. So we get the hypervisor to do that. Sorry, the PVM firmware to do that if we are a debuggable VM, which will change the identity of the VM. And you can't use those in production, but it's useful for development. All right, let's see where we are with upstream. Well, actually, we're in a pretty good state. The restricted DMA went up a while ago. I was working with the Chrome OS folks on that. The open dice stuff, we have a miscellaneous device that exposes that CDI chain to user space. And it allows user space to wipe it as well, so you don't leave it hanging around in memory. The hypercore discovery is upstream. The memory sharing just went in this merge window, so we can do the SWI-TOB stuff and actually share the memory back. The GIC ITS, which is our interrupt controller, has some tables that need to be shared, and it doesn't use the DMA API. There are patches on the list for that, undergoing review. I've tested them, they work. So hopefully they'll land soon. MMIO guard, we've hooked into IO remap, so that's upstream as well. And then there's a few optional drivers. So I mentioned the enlightened VirtIO balloon. We haven't posted that, maybe we should. There's a per CPU stall detector we added. That's upstream. And then there's a interesting vCPU freak device for plumbing the guest scheduler into the host uclamp setting. So you can, these things run on batteries, so we have to be careful about perf and power. And yeah, the new code is in this directory. It's very short because it basically just uses hooks in the architecture backend, which have been designed so they can be reused by the ARM CCA stuff. So hopefully we can all share the common infrastructure for this. Okay, I've got a really, really simple demo because I read my abstract when I was writing my slides this week and realized I'd promised a demo. Luckily, Mark kindly brought a device with him, so I've got a Pixel 8 here, and I've managed to flash it with AOSP, and yeah, I can just sort of, I have to do it one-handed because I've got this microphone, but let me just put it down a second and I'll switch to some terminals. Okay, let's see if we can get a root shell. Okay, so this is a Pixel 8. On the right-hand side is an ADB root shell on the device. And you can see, sorry, I'm really bad at typing with one hand. You can see it's a quite old kernel, as you might be used to with Android handsets, but it's a 5.15 based kernel. It's Android 14. And this is unmodified, right? This is a production, all right, it's a user debug build, but it's still an official Android kernel that you would, if you went and bought a Pixel 8, you'd probably have that running on it. Okay, what can I show you in here? I've got a few minutes. So we go into the Apex directory. The place where all the virtualization stuff lives is in android.virt. Okay, you can see, here's all the stuff that Android is going to use under the hood for doing virtualization. So for example, you'll recognize in bin, we have a cross VM binary, okay? But we also have this VM binary. And let me make this bigger. There we are. Oops, not list. Oh. So there's a bunch of stuff here, utilities for creating new VMs. I mean, this is not what you would normally use, right? This is for development. So we got the run microdroid where it just gives you a pre-canned microdroid. So let me try and run that. If I get out of this shell, I've got some scripts in here. What are my scripts called? I've got a spawn VM. That sounds helpful, doesn't it? Okay, so spawn VM is going to basically invoke that run microdroid with a -p, which means run it as a protected VM. So hopefully this will work. Spawn VM. Okay, so this is now booting a protected VM, and it's got an empty payload, so it's just sitting there doing nothing now. But if we, maybe I'll make it full screen again. If we scroll up, yep, no problem. You can see here it did some dice derivation. That's using the device, the miscellaneous device I was talking about. And we've got at the top here, so these errors, which you don't need to worry about them, I assure you. These errors are coming from PVM firmware. Which is here. It even says, look, please disregard any previous error. So we don't need to worry about it. It's honest. but yeah, that's pVM firmware, which runs first, right? And then the VirtIO console kicks in. VirtIO console kicks in here. So we've missed the first part. So if I go back down and I get out of this, I should now be able to get a CID for that. So it's again, I said all the binder stuff goes over VSOC. So we've got CID 2048. So I can, oops, sorry, one hand. I can get a shell on that VM. 2048. Okay, here we are. So I'm now in the VM. And you can see it's an unmodified middle of the merge window. You can look at that commit. I think it's the LSM merge. So it's from Wednesday when I was at Plumbers. So it's cool. We're running an unmodified upstream kernel as part of our microjig guest. So we've made it. It's great. And that's basically it. I promised a demo. There's not a lot going on. You can see the VirtIO devices. There's the vCPU stall detector. I suppose if we look at the full D message. Oops, sorry. Look at the full D message. You can scroll right back to the top. You can see it probing everything up here. Here's the 611 kernel. Here's the restricted DMA pool, for example. Here are the hypervisor calls. So there's quite a few of them. Even the misfits are here because it's an Android host. And then down in the PCI layer, we start using this bounce buffer. I mean, yeah, it's just kind of, if you didn't have the patches, it wouldn't have done anything. So there we are. It's you can run a mainline kernel on your phone, sort of, and that's basically it. So I think I've got a couple of minutes for questions, if anyone has any. Alex. You can have this one.
So for your VirtIO devices, you've got this bounce buffer.
Yeah.
So you have to copy stuff. You allocate memory and then copy it into the bounce buffer to do the transaction. Is there any possibility of doing the allocation directly in the bounce buffer so you can avoid that copy?
Yeah, that's right. So that's a good question. The V-rings themselves are allocated in there. So if the DMA alloc coherent API, when you're doing an actual allocation, will allocate directly from those bounce buffers. The problem comes when, for example, the network layer gives you an SKB, which I allocated 1 million years ago. So I want you to transfer this, and it's not a page size, it's not aligned and things. You can't just share the whole SKB because there are things like pointers in there, which you don't want the host to be able to manipulate. So in that case, you have to bounce the data through the SWIO TLB. But the ring itself is allocated in there from the beginning.
Thanks.
I assume you've got some sort of, I realize your talk is on the guest side, but I've actually got a host side question, if you don't mind. I realized that you've, you probably have an IOMMU.
That's right? True. Yeah, well, we don't always, but we do have DMA protection hardware. So it can't always translate. Okay. That tends to be okay because we're not doing device pass-through at the moment.
Right, but still, I mean, that IOMMU data page tables needs to be owned by pKVM, right?
Yes,
and so when you donate memory, what do you do with the IOMMU to ensure that remains confidential?
Yep. That's a good question. So initially we thought, hey, what we're going to do is we're going to force everybody, we're going to assume that everyone has built the latest ARM architecture SMMU, and if they haven't built that, then we won't support it, and we'll have a driver for that. But this is it doesn't really work, right? Because none of the devices have done that yet. So we thought, okay, what can we do? So we have added we've extended the kernel modules, so you can load modules into the hypervisor early during boot. So we have a way that you can load modular code, and unlike a kernel module, you can't just call any code in the hypervisor. There's no export symbol, okay? So when you register, you get when the module initializes, you get a structure function pointers, and you can choose to register. You can say, hey, I'm an IOMMU. I'd like to register myself. And then there are callbacks. So when the host pages change state, we call back into the IOMMU drivers.
And that goes through pKVM?
That's all at EL2, yeah. So,
okay, that's
so basically the host will, for example, to give a concrete example here, imagine you get a guest exit back to the host, and it says, look, I've taken a page fault. I need you to give me a page. The host is going to go and magic up that page. It's going to issue a donation hypercall to the hypervisor. And at that point, we're going to go and update the CPU page tables, and we're going to call into those IMMU drivers to say, can you make sure that this isn't mapped anymore, please?
Could you tell us a little bit about that enlightened balloon thing?
Yeah, sure. So it's, I mean, we're basically using the balloon driver as is, except okay, if we didn't change the balloon, the guest is going to put the address of the page, the GFN, whatever it is, into the ring, right? CrossVM is going to pick that up. It's going to do the advise. But there are two problems with this. First of all, there is a long-term gup pin on that page because we don't have guest memFD yet. We're doing anonymous memory right now. So there's a long-term gup pin on that page, so the advise isn't going to do anything. And secondly, if it tried to access that page, it would fault. It would be fatal because it doesn't have it back. So the only change we need, and I think we shouldn't upstream this until we figured out the guest memFD story because it's likely going to be different. But the only change we need is to make sure that that guest balloon driver, before putting the GFN in the ring of the balloon, it has to issue a hypercall to say, hey, I don't want this page anymore. You can give it back to the host. Does that make sense?
Jumping back to your IOMMU madness, how do you foresee anything beyond the IOMMU getting shoved into pKVM, into the hypervisor part? And if so, how do you avoid re-implementing module support in a very sketchy ad hoc way?
Yeah, so I mean, you can look at the struct that we currently have for modules, and sadly there is more than just the IOMMU hooks. Some of this is a pragmatic decision, so because we want to ship this, right? So this is shipping right now. It's not a made-up thing, right? So we have millions of VMs a day.
More from an
right?
upstream perspective.
Yeah, so
I can't imagine you want to do this.
Yes, you're completely right. So I think for upstream, we might do some of the module support, but I think we would limit it to IMMUs. And there's one good reason for doing that, which is that having a hypervisor where you have, say, 15 different IMMU drivers built in is also bad, because it's a lot of code that's just sitting there. So the module interfaces allows us to get away from that and just load the actual privileged driver for the device we have. I think that's a worthwhile use of that infrastructure.
So when you say only IOMMU code, do you anticipate relying on policy to prevent the pKVM layer from exploding in its TCB, or are you going to technologically enforce that somehow?
Yeah, so we have a point during boot where we prevent, it's quite early during boot, we prevent any modules being loaded after that point. And if you haven't loaded an IMMU, we clear the PVM firmware, so you can't run protected VMs. So we basically trust the host kernel during boot, during early boot.
But how do you trust it to only load IOMMU drivers?
The same way so it's a slightly different for Android. You have to trust the people that make your phone. There are lots of other reasons for that as well.
Okay, you trust the person that built that. Okay.
Yeah, and everything's verified coming off the flash, so it's you haven't run anything else that wasn't verified at that point. So
the short answer is, from an upstream kernel perspective, it's policy to not support arbitrary modules loading the TCB, but technically, from a technical perspective, you could, in theory, if you wanted to do something crazy.
Yes, you could. I mean, so we have debug options where we just don't close the door because it's useful for testing some of this stuff, right? Oliver, and then I think we've got lunch, so make it quick.
Yeah, do you have a use case for actually sharing the GIC ITS tables with the host? Because at least in upstream KVM, the ITS state is just maintained in KVM and not in guest memory.
Are you sure?
Yes.
Because okay, so maybe I'm talking about the wrong thing. But if you don't do this, then the host kernel does like a get user, and it will fault. So.
We use the configuration table from the guests, and that's the important bit. We don't. The KVM doesn't really make the difference between redistributor and ITS. It's one big pile of shit.
and the motivation for that, because wired interrupts work fine, but MSIs perform so much better because we avoid the I/O traps back to the VMM. So,
thank you.
You all look really hungry, so we should go and have some lunch. Thanks very much.